Alright, this video is going to go through the last 10 questions of the in-text questions of chapter 18. So we'll be starting with question 1. If you need questions 1 to 9, check the other video. Alright, question 10 reads, in each of the cases shown in figure 18.7, which is off to the side there, a light ray travels from a substance X to air. Find the refractive index of the substance. Okay, so if we look at the first one, I'll draw the diagram for each of these as we work our way through. We have our material, we are coming in at 30 degrees, we are leaving at 45 degrees, which matches what we'd expect. We're coming from a more dense to a less dense material, and air in this case should be the least dense. With an n of equals 1, we should expect to see that the light will bend away from the normal. So we know that this is air, so hence n equals 1, and we don't know what this is, and n equals don't know. So let's list off what we've got. Incident angle equals 30, refracted angle equals 45, initial material equals not sure, secondary material equals air. This is Snell's law. N1 sine theta 1, N2 sine theta 2. Let's substitute. N1 sine 30 equals 1 times sine 45. So N1 equals sine 45 over sine 30. Chuck it on our calculator. Let's see, sine 45 divided by sine of 30 gives me n equals 1.41. Let's keep going. B, same thing. Now, because we're the same situation over and over, all we're doing is we're changing the angles. We're still ending up in air. I'm going to use this formula here now, from now on, as our derived relationship we need for this situation. Sometimes remembering or recognizing these sort of things in a question really speeds up the processing time you need to do. You don't need to write these steps over and over. Or if we did this rearrangement first with algebra to get that n1 equals n2 sine 2 over sine of 1, then you go, alright, well now we can just use that over and over and over again and skip a couple of steps. That sort of being comfortable with math in that way is really useful for physics problems. Okay, so another situation. Let's see. We have light coming in, 30 degrees. Note where the angle is, 10 degrees. So remember, we need our incident angle, which is between the normal and the ray. So that's going to be 60 degrees. And we need the light between the refracted ray and the normal is going to be 80 degrees. We're dealing with air, so n equals 1, and we have substance X, n equals don't know. Let's list it off. So theta 1 equals 60, theta 2 equals 80, n1 equals don't know, n2 equals 1, and we saw before that n1 will equal sine theta 2 over sine theta 1. It's multiplied by n2, but n2 is just air. So n1 equals sine of 80 over sine of 60. Chuck it in. Sine 80 divided by sine 60 gives me 1.13. 1.14 if we round it off. Next numbers are 7. Okay. On to our next. This time, though, we're not given an angle, we're given a velocity. Okay, so remember, we're trying to find the n of a medium. So the n of that medium, remember the original definition is not using Snell's law, but is defined as the ratio between the speed of light in air and the speed of light inside the material. So here we have v equals 2.4 times 10 to the 8, we'll say it's v in x. And here will be in air equals c equals 3 times 10 to the 8. So n equals c over v equals 3 times 10 to the 8 over 2.4 times 10 to the 8 equals 3 over 2.4. 1.25. Now, on a question, I probably wouldn't expect to see this little step in your writing. I don't need to see that, but you should recognise that, yeah, we've got 10 to the 8, 10 to the 8, the cancel, and just save yourself some time and the hassle of making sure that your calculator's done the right thing. And just go, well, 3 over 2.4, we've got the correct answer. And our last one here, we've got a new symbol there, theta c. Now theta c in this case, they're saying the critical angle, we're talking about total internal reflection there. When does the light, the refracted light, instead of refracting out into the medium, instead skim across that barrier. So we've got our setup again, we come in at 47 degrees, and now the refracted ray goes off there. Still needs Snell's law, we can still do it with that. So we've got n equals, don't know, what's this angle at? Not this angle. It's going to be 90 degrees. So, sorry, that was my phone, if you could hear that. So let's list it off. We've got theta 1 equals 47, theta 2 equals 90, n1 equals, don't know, n2 equals 1. Now, let's substitute that in, so we remember n2 equals sine, sorry, not n2, n1 equals sine theta 2 over sine theta 1 in this instance. We're multiplying it still by n2, but n2 is just 1, so we can ignore that. So n1 will equal sine of 90 over sine of 47, and sine of 90 is equal to 1, so that just equals 1 over sine 47. So 1 divided by sine 47 equals 1.37 or 1.36. Textbook gives us that as 1.37. Yeah, there's the rounding. Okay, so that is question 10. Question 11. And you can see in all these, except for C here, that was an application of the definition. Even in this special situation, it's just Snell's law. You don't have to remember a bunch of different rules going, oh, if total internal reflection used this rule, it's always Snell's law, just some things have been cancelled off, so they try to dress it up in a different way and say, oh, you've got to remember another formula and another formula. It's Snell's law. It's just the same law over and over again. Alright, if you can remember the basics, then you don't need to remember 50 different special cases, you just use the basics really well. Okay, so we've got a question here, layer of water, n of water is 1.33, it's placed on a block of glass, n of glass is 1.52, as shown in the figure below. Calculate the angles. Well, this is just the same as that question 9 that we saw before, so let's draw that up. There's our water, there's our glass. So n equals 1.52, here's our water, n equals 1.33, and we have light coming in. We are given the incident angle of 38 degrees. Okay, it's coming in from a less dense to a more dense medium, so it's going to bend towards the normal. And that angle, whatever it comes out as being, will be the same as that angle. So this angle here, will be, so I'm just making sure you can see this, that angle there will be the same as that angle there after we've calculated the two angles. Remember, these are parallel lines, so Z rule applies. And then after that, again, less dense to a more dense medium, it'll bend towards the normal again, and that's the second thing that we need to work out. So let's list off. Theta 1 equals 38. N1 equals, well, what is it? It's air, so N must equal 1. N2 equals 1.37. Theta 2 equals dunno. So N1 sine theta 1 equals N2 sine theta 2. 1 times the sine of 38 equals N2, oh, sorry, 1.37. Thought we were still doing the previous type of questions. Sine of dunno. So rearrange that, we get that sine of dunno equals sine 38 over 1.37. So if we take the arc sine then, arcsine of sine 38 over 1.37. Sine 38 divided by 1.37. Take the arcsine. We get that this is 26.7 degrees. Now, as we said, that angle now becomes our new incident angle. So here, this angle we just calculated 26.7. That becomes our new incident angle for the next barrier, because, said rule, parallel lines, we have a transversal connection, therefore opposite angles, internal opposite angles must be equal. So let's put that in then. So theta 1 equals 26.7 degrees. N1 equals, well, that's going to be our water, 1.33. N2 is our glass, 1.52. Theta 2, we don't know. So Snell's law again. N1 sine theta 1 equals N2 sine theta 2. This time I'm going to do the rearranging before I do the substitution. I'm trying to find theta 2 on its own, so let's do that. N1 over N2 sine theta 1 equals sine theta 2. And theta 2 must then equal the arcsine of N1 over N2 sine theta 1. There's no difference between doing before that, but sometimes things cancel and it means less math to have to do, which is always good. So let's substitute that. Equals sine of N1, 1.33, N2, 1.52, sine of, and that was 26.7, wasn't it? Chuck it in. Sine 26.7 times 1.33 divided by 1.52, and take the arc sine of that answer, and we get that theta 2 equals 23.1 or 0.2 degrees, depending on how the book rounds it. Alright, and again, we expected it to bend towards the normal because it's going from glass, so water into glass, so less dense to more dense. Okay. Let's hit 12. In which of the following will rays of light bend towards the normal? Oh, well, this is going to be similar to what we just talked about. So A, glass, to water. Will it bend towards the normal or away from the normal? So we just did water to glass and we saw it bend towards. So if we go in the opposite direction, glass to water, then that's going to bend away. B, glass to diamond. Okay, diamond is one of the most dense matters or types of material. If you go back to that table right at the start of the chapter, the 18.1 table that we used for a couple of questions, we would see, well, diamond's got an N of 2.4, glass was an N of about 1.5-ish, so that means that diamond is more dense, so it would bend towards. C, alcohol to water. Okay, I don't know the alcohol volume straight off my head, so I'm going to go back up that table. Table 18.1. Okay, we've got ethyl alcohol here, and we see that ethyl alcohol has an N of 1.36, water has an N of 1.33 according to table 18.1. So if we're doing this one, so this is N equals 1.36, 1.33, it's going from more dense to less dense. It's only slightly, but it's still away. And D, perspex to heavy flint glass. Okay, well, let's hang on, I've just scrolled here. Perspex to heavy flint glass. Here we go. Perspex has an N of 2. Heavy flint glass has, oh, sorry, not 2, that's the speed of light. Perspex has an N of 1.49. and heavy flint glass has an N of 1.65. So that must mean this is more dense than this, so we're going from a less dense to a more dense, so we're going towards. Okay, so if we're going an increase in density, we're going to end up seeing it bend towards. If we're going away from density, then we end up seeing it get less. Let's go to the next question. Oh, I was looking at 14. Yeah, B and D, the only ones that do. 13. Okay. A student on a biology field trip dropped a coin in a creek. The depth of the water appeared to be 75 centimetres, so he rolled up his sleeves to retrieve the money. What would be the consequence of such an action? Explain. And the reminder is the refractive index of water is 1.33. Now, this isn't something we cover in this unit specifically, but it's not a hard... We can sort of think about that happen. If we scroll up a little bit from this question, we see that there is a worked model for how to calculate true depth and apparent depth in relation to n equals n values. So the depth of the water appeared. This is not a true depth. This is a appeared. Let's go with it x a. A in this case is substitute for appeared, and x is a common thing we use for measuring length, and that's 75 centimeters. Okay. Because this is unitless, whatever unit I use here, that'll give me the unit for the answer. And I want to know, well, what is x true? I don't know what that is. Okay. And the formula they've given us there is that x true over x appeared equals n. So let's substitute. X true over 75 equals 1.33, and so we're just going to multiply these two together. X true 1.33 times 75 is 99.75 centimeters. So what will happen? He'll get his sleeve wet. Okay, he thinks that it's only 75 centimeters. He's rolled up his arm so that he can go in, but it's going to go a bit further if he wants to get his coin. Now, there is quite a good diagram right above that. It's worthwhile just have a look at this to understand the idea of what's happening with apparent depth and true depth. And that's why when we've seen those pictures of things bending in light, we see this weirdness happen. But we don't need to worry too much about that for now. This is the only question on that as well, so don't stress. Next stuff is internal refraction and other types of refraction. 14. Each of the following situations where a light ray passes from one medium to another, state whether it is possible for total internal reflection to take place, and then explain. So let's start with the explaining of it first. Remember, total internal reflection happens when a material refracts so much away from the normal that instead of leaving the material, it comes back into the original material. So when does something refract away from the normal? Okay. To refract away from a normal, we need to go from a more dense to a less dense material, like water into air that can have internal refraction, or from diamond into air. Okay, that's a really big example because we know diamonds sparkle because of total internal refraction or reflection. And fiber optics, they do the same thing because the density in the inside is less than the density on the outside. The light bounces inside the wire. So let's go through our examples. Air to glass. So a n of 1 to an n of 1.52. Well, note this is increasing, so no total internal reflection possible. B, diamond to air. So diamond to air. N is about 2.4. N equals 1. So yes, TIR is impossible because we're going from a more dense to a less dense material. Let's keep going. C, water to glass. So N equals 1.33, N equals 1.5, so there would be no possible TIR, less dense to more dense. D, flint glass to air, n equals 1. Let's just use the heavy flint glass we had before. That was about 1.8. Regardless of which, we can see it's going to go from a more dense to a less dense. So yes, there is TIR. Okay, E, ice to a vacuum. Okay, ice to vacuum. I don't know what ice is off the top of my head, but it's just water. So let's just use waters, because vacuum is n equals 1, isn't it? And ice, let's say it's maybe a bit bigger than 1.3. What I do know, though, it's not going to be below 1. So this number is a guesstimate, but the fact that I know where it's going to doesn't matter, means it's not important. So 1.33, so yes, you could get TIR. And finally, crown glass to perspex. Crown glass, sorry, my handwriting's terrible there, to perspex. Well, that was n equals, I'm going to have to scroll that one up, I'm not sure on either of those, so let's go back to our table right at the top. I may as well check ice while I'm there, actually. Oh, ice was 1.3, a little bit less. Oh, yes, I suppose ice is less dense than water, isn't it? 1.3. The answer is still the same. Perspex was 1.49. And crown glass is 1.52. So, yes, you could get TIR happening because higher number to smaller number. Okay, so the rule is if N1 is greater than N2, then TIR is possible because it refracts away. Okay, let's move to the next 15. A block of ice. A block of ice is placed on top of a semicircular block of crown glass. Figure 18.5. Okay. At what minimum angle would all light incident on the boundary between the two surfaces be reflected? Okay. So, well, we've got those things. So, crown glass. So, n of G would equal 1.52. And n of the ice equals 1.3. We saw that before, so we'll just use those numbers. And the diagram kind of looks like this. So we've got that block of ice, and it's sitting 90 degrees on our semicircular thing, and the light is being shone in through the side. So we don't care if there's any bending here. All we know is that the light is coming in here, it's hitting this point, and we want to make sure that it bounces backwards at the same angle. Okay? And it will. If you have an angle that is higher than the TIR threshold, then it will come back at the same angle. So we don't need to worry about calculating the reflected angle is going to be the same as the incident angle. And we don't care about what's going on over here. So, what we really want to know then is what angle do we need to shine this in at so that the refracted angle goes off at 90 degrees, because then just a little bit past that will make it totally internal reflect. Okay, so let's let theta 2 equal 90 degrees, and we want to know, well, what is theta 1? Okay, so that's Snell's law. We've got two n's, we've got two thetas. Let's Snell's law it up. N1 sine theta 1 equals N2 sine theta 2. So N1 was the glass, that's 1.52. Sine theta 1 equals N2, that was 1.3. Sine of 90, and remember the sine of 90 is just 1. So sine theta 1 equals 1.3 over 1.52. And so theta 1 equals, there's my calculator, 3 divided by 1.52, take the arc sine, we get that it is 58.78, so let's round it up, 58.8 degrees. At 58.8 degrees, it'll start bouncing back because it's rounded up just a little bit. All right, and if you have a think about this, then we can sort of extrapolate the total internal reflection rule is sine theta, and we give it theta c to say it's the critical angle, equals n2 over n1. So that's something that a lot of books recommend and say, oh, you should know that. You derive it from Snell's law, so you don't need to memorize it, but if you recognize it, you can save yourself a bit of time. Where were I? 16. A ray of light travels from one medium to another. It is found that total internal reflection occurs when the incident angle is greater than 54 degrees. If the refractive index of the first medium is 1.49, calculate the refractive index of the second medium. All right, well, let's use this. So what we've got there is a critical angle. When it's greater than 54 degrees, that's the critical angle. All right, we know that the first medium, N1, equals 1.49. We want to know what is N2. Okay, so let's just use what we derived a second ago. Sine theta c equals N2 over 1.49. Oops, so sine over N1. Let's do our proper substitution methods. Okay, so we're going to have N1 sine theta c equals N2. So that will equal 1.49 times the sine of 454. Sine 54 multiplied by 1.49. We get that equals 1.21-ish. Okay, it's less than where we started, so that means yep, we're definitely getting the right sort of idea there. Okay, 17. Students investigating total internal reflection using a semicircular block of glass notice that before total internal reflection occurs, there is a faint reflected beam. Comment of the intensity of beams 1, 2, and 3 in figure 18.16 as the angle of incidence increases. So let's draw our diagram. We have our semicircle. We have our point of impact. Here is our angle of incidence. And this is beam 1 here. We have beam 2 bending away from the normal because, you know, it's, what's what I'm looking for? More dense to less dense. And we have a reflected line, coming here as well. That's beam 3. Okay, so beam 1, it's going to be unchanged. It's the incident angle. Okay, nothing will change about that. Imagine using the lasers we have in class. I mean, we might do this one in class next week just to sort of get an idea of it. But if we're shining that in, if we're shining this beam in, that's just coming from our laser. Okay? 2 and 3 though are going to change. So 2, if we keep making this angle bigger and bigger, eventually this is going to refract down into this. Okay? But total internal reflection is not this perfect it either happens or it doesn't thing. You get a little bit of it beforehand. If you play around with the lasers this week, have a look to see what happens at the boundaries. It's not always a full, oh yeah, everything just deflects out. Little imperfections in the glass can cause a bit of extra refraction. Dust on it can affect it. It's never perfect like the math wants it to be. There's always a little bit of just aberrations on there. So some of it will start refracting a bit earlier, but then as we keep increasing the angle, then we get more and more refraction happening as more and more light hits that critical angle there as the photons from the laser hits the interception. So this too would end up getting reduced over time as less light escapes, and this one would get more intense. Intensify because more and more light eventually gets refracted back inside or reflected back inside. 18. Wait, here we go. So now we're talking about some practical applications of total internal reflection. So optical fibers have a less optically dense layer surrounding the fiber so as to produce total internal reflection. That's what we've been talking about. If the fiber has a refractive index of 1.7 and the outside cladding layer has a refractive index of 1.48, calculate the minimum angle at which light incident on the junction is totally internally reflected. So it's just saying when light hits the boundary where the two things touch, what minimum angle do we need? Secondly, what is the speed of light in the fibre? So we've got two formulas we need to think about here. So one, let's list what we have. N1, because that's where our light is starting, is 1.7. N2 is 1.48. We want to know what is the minimum angle, so we need to know what happens when theta 2 equals 90 degrees. That way we get the minimum angle, or we could have used that derived one we had before. I'm going to use Snell's law and just do it from first principles. So N1 sine theta 1 equals N2 sine theta 2. Well, we want to know what is theta 1 originally. So let's rearrange that. We get that sine theta 1 equals N2 over N1 sine theta 2. Sine theta 1 equals 1.48, 1.7 sine of 90. So that means theta 1 equals the arc sine of 1.48 over 1.7. Arc sine, we get about 60.5 degrees. Okay, so that's the first bit. Second part was, well, what is the speed of light? Okay, well, the speed of light in the fibre. And remember, the fibre in this case is that 1.7. Well, that's going to be our N equals C over V. We know the speed of light. So let's do our rearranging. We get that V will equal C over N equals 3 times 10 to the 8 over 1.7. So let's chuck that in. 3 times 10 to the 8 divided by 1.7 gives me 1.76 times 10 to the 8 meters per second. If we double check our answers there, question 18 we're doing, yep, 60.5 we got, and 1.76 times 10 to the 8. Great. Both practical applications of the theory we've learnt before. Optical stuff's pretty important. Last question. A scuba diver working in the ocean looks up to notice the sun is setting on the horizon. At what angle to the normal to the surface will he need to look? Okay, so let's think about that. We've got our scuba diver down here. We've got the water at the top. And the sun is setting over the side. So he looks up and he sees the sun. Let's assume that it's total internal reflection because we haven't been told a second angle. Okay? So this must mean, well, what is this angle? Okay, to the normal of the surface, so we want to know the incident angle. We don't want to know how high he looks up. We can certainly figure that out. We're asked what is the angle to the normal of the surface, so that is the angle we care about, not that one. We're told N of salt water is 1.38, and that's air, so that means N equals 1. So we know that the critical angle equals N2, so N2 over N1, yep. N2 was air over 1.38. So theta C will equal the arc sine of 1 over 1.38. 1 divided by 1.38. Take the arc sine. And we get that he gets an angle of 46.4 degrees. Okay, so this is the last question for the in-text ones. 1-star and 2-star questions will be in a further video. Thanks guys, bye.